Hello everyone, this is Abilino Dawes, your instructor. Now in lecture 10, now we have discussed three-phase short circuit, and we know that short circuit currents are at high values, which if not interrupted, will cause damage to our equipment, the generators, the transformers, and so on. So uh, in this lecture, we will be considering the power circuit breaker, which will protect our equipment from damage due to short circuit. Of course, the power circuit breakers operate with the relays and the instrument transformers like CTs and the PTs. So for the circuit breaker, we consider the basic ratings. Now, the first one is the rated voltage. The rated voltage of a circuit breaker is the nominal voltage class. Where the circuit breaker is intended to be placed, not to protect an equipment. So, uh, if the circuit breaker is to protect a 138 kV equipment, then its rated voltage should be 138 kV. Or if it will protect 69 kV equipment, then its rated voltage should be 69. Or when it protect the 13.8 kV equipment, then its rated voltage should be 13.8. So, the nominal voltage class will be the voltage rating of our power circuit breakers. Now, the second is the rated continuous current. This is equal to the I rated of the PCB, meaning it is the current that it continuously carry 24/7. So that is its rated current. In other words, it can the circuit breaker will be able to sustain this amount of current that will flow without interruption. Okay, now the third is the rated short circuit current. Now, this rated short circuit current is equal to the sub-transient fault current, and we call this as the symmetrical fault current. Okay, when we use the sub-transient reactance of our generators, to get the short circuit current. So it is this, the sub-transient fault current. Okay, the rated short circuit current of our PCB. Then another important rating is the rated interrupting current of our power circuit breaker, which sometimes is called momentary current rating of our circuit breaker. And this rated interrupting current is just equal to 1.6 times the sub-transient fault current IF double prime. Now this zero point 0.6 or 60% of the subtransient current will take care of the DC component of the short circuit current, now which is decaying. Uh, in other words, it will decay at its appearance during the at the time of a short circuit. Okay, after a few cycles, it will this DC component will disappear. So at the beginning of short circuit, the highest DC component is about 60% of the symmetrical fault current IF double prime. So it is that what we call as the momentary current rating. 1.6 times the subtransient current fault current. And then the next important rating which we specify to our circuit breaker is its rated interrupting capacity. Now, this interrupting capacity is in terms of MVA, so it is the apparent interrupting capacity, S or in MVA, and this interrupting capacity would just be equal to square root of 3 times the line to line voltage nominal times the momentary current rating from here. So momentary current times square root of 3 times the nominal voltage or the rated voltage of our circuit breaker. And then the next one is the rated maximum voltage. Okay, the maximum voltage would be 5% over its nominal voltage. So whatever is the voltage rating of our power circuit breaker, then we just add 5% of that. That will make the rated maximum voltage. And of course, the rated frequency should be also is specified. So these are the most important rating, no, that we should specify to our power circuit breaker. Now let's have an example here. Where we have another case of a three-phase short circuit. It says here that an unloaded three-phase generator shown generating its rated voltage is shorted at its terminals. Calculate the fault current during the sub-transient, transient, and the steady state condition in per unit and actual. So we have a very simple case here. We have a generator and it is running. And then it is unloaded. So there is no load connected to the generator at its bus, but its terminals are short-circuited. So well, the KVA rating of our, no, MVA rating of our generator is 25 with terminal voltage of 13.8 and the generator is Y connected, solidly grounded. Now its subtransient reactance XD double prime is 0.08 per unit and its direct uh, access transient reactance XD prime is 0.14 per unit and its synchronous reactance XD is equal to 0.2 per unit. So take note that the subtransient reactance is the smallest, then followed by the transient reactance which is 0.14 and then steady state, no, reactance of our or synchronous reactance of our generator is the largest of 0.2 per unit. Now since we learned in lecture 10 that for a three-phase short circuit we only consider the positive sequence impedance diagram. Now so the zero sequence diagram will not be considered, as well as the negative sequence impedance diagram. So the positive sequence impedance diagram of our generator up to its terminal would be this, no, where we have a generated voltage per phase of 1.0 at an angle of 0 per unit as our reference, and then this is in series with its positive sequence reactance. We just call this as GX, and then we have here the terminal and the fault occurs here now. So the fault current IF will be flowing towards the fault. Now actually it is understood that this terminal A for phase A is actually shorted towards the ground. So well, anyway, we can just represent our short circuit as X here, no, meaning this terminal is shorted towards the ground, so that we have here a complete circuit and fault current flows this way. So since our impedance network is very simple, so well, we can immediately determine the fault current here, IF, and this is just equal to the voltage E sub A divided by the reactance of our generator GX. So for subtransient fault current during the first cycle, the fault current IF double prime will just be equal to EA over GXD double prime. or this is equal to 1.0 at an angle of 0 divided by gxd double prime, which is j 0.08. So substituting the values, we get 12.5 at an angle of minus 90 degrees, okay, per unit. No? So this is the value of our subtransient, okay, fault current IF double prime. Now for the transient fault current, which is which occurs at between 3 cycles to 6 cycles, okay, our subtransient fault current IF prime is equal to EA, and then the reactance of the generator is changed, okay, into XD prime. So substituting the values, we have, okay, XD prime is 0.14, and so we have, okay, per unit value of 7.143 at an angle of minus 90 degrees, okay, per unit. Now at a steady state fault current, which is from 12 cycles to 120 cycles. So in this case, okay, the fault current here has stabilized, okay, to a constant value, because during this time, okay, the graph of the fault current, okay, has stabilized. So the okay, the steady state fault current IF would just be equal to EA over XD of the generator. So substituting the values for XD, we have 0.2 and our A equal to 1.0, and then computing, we have, okay, the steady state fault current equal to 5.0 at an angle of minus 90 degrees, okay, per unit. So okay, among the three, okay, our subtransient fault current is the largest, and then the transient, okay, fault current is in between, and our steady state fault current is, okay, the smallest. Now, computing for the base current at our generator side, okay, this our base current is just equal to is base, okay, 3 phase divided by square root of 3 times the voltage base line to line. So substituting the values, our is base is just the MVA capacity of our generator, and then our voltage base line to line is 13.8, and so therefore our base current will just be equal to 1.0, okay, 45.924, okay, amperes. So the actual currents, therefore, okay, for our subtransient fault current IF double prime, so it is equal to its per unit value of 12.5 times the base current of 1045.924 amperes. So our subtransient fault current is 13,074 amperes. And our subtransient fault current would be the per unit value of 7.143 times, okay, the base current. So we have 7,471 amperes. And our steady state fault current, okay, with its per unit value of, okay, 5.0, we multiply this by the base current, then its actual value is 5,000, okay, 229.6, okay, amperes. Okay, so if we have to graph, okay, the short circuit current as time, okay, proceeds, now from the start of the short circuit, which is at t equal to 0, so it is on this axis. Okay, so the graph of our short circuit current looks like this. So it's decreasing, okay, bounded, it's sinusoidal, but it's decreasing in magnitude. Okay, so enclosed by this exponential envelope. You know? So the value here is our IF subtransient fault current IF double prime, and the value of the fault current here, okay, 3 to 6, okay, cycles is our IF prime, no, subtransient current. Okay, where of course, okay, now for the transient, subtransient, okay, fault current, okay, we have the okay, reactance of our generator, which is XD double prime. And at subtransient condition, okay, our generator changes its reactance, okay, from XD double prime to XD prime, okay, with XD prime greater than the value of XD double prime, and so we have the short circuit current IF RK prime as the sub transient RK fault current. Now from 12 cycles to 120 cycles, okay, the fault current has stabilized, okay, to this level. Okay, so the fault current here has remained, okay, constant, and we call that as the, okay, steady state, okay, fault current IF with subtransient reactance, okay, XD, okay, of our generator. Okay, so this is this subtransient time, okay, about one, okay, cycle to 3 cycles. And then for our, okay, transient time, okay, from 3 cycles to 6 cycles. And then for our steady state, okay, we have, okay, 12 cycles to 120 cycles. Okay, so uh, in the example, no, in the preceding example, okay, we have to specify, okay, the ratings of the power circuit breaker, okay, that will protect, okay, our generator. Okay, so specifying, okay, the circuit breakers to protect our generator, we have, okay, this basic, okay, ratings of our circuit breaker. Okay, one is, okay, the rated voltage. Now since the generator is rated 13.8 kV, so our circuit breaker also should be rated, okay, 13.8 kV. Now the rated continuous current of our power circuit breaker, I rated here, would be equal to the continuous current. So it is the MV rating of our generator divided by square root of 3 times, okay, the line-to-line voltage. So substituting the values, okay, for MV rating of our generator, change to kVA, so 25,000 kVA, where square root of 3 divided by 13.8 kV. So kV and kV cancel, so we have amperes, okay, remaining. So the rated continuous current of the circuit breaker, okay, would be equal to 1000, okay, 46, okay, amperes. Now for its rated short circuit current, it is just equal to, okay, the sub-transient fault current or symmetrical fault current IF, okay, double prime, which has an actual value of 13,074 amperes. Now for its rated interrupting current or the momentary current rating, it would just be equal to 1.6 times the subtransient fault current. So multiplying 1.6 by this, okay, it gives us 20,918 amperes. Now for its rated interrupting capacity, okay, it is equal to square root of 3 times the line-to-line voltage nominal times the momentary current rating. And so substituting the values, you have square root of 3 times 13.8 kV, okay, times 20.918 kiloamperes. So the interrupting capacity of our breaker should be 500 MVA. Now, the rated maximum voltage or kV max would be, okay, 5% over the rated voltage, or that is equal to 1.05 times 13.8 kV. So it is equal to 14.5 kV. So this is the maximum, okay, voltage that our circuit breaker should be subjected to. And then, of course, the rated frequency, okay, if we are in the Philippines, then this is equal to 60 hertz.